Good morning, everyone. Thank you for coming to this topic on API security. My name is Eoin Woods. It's very nice to join you this morning to talk about security. This morning, we're going to explore the state of API security, and we're going to talk a bit about software security in general. And then the core of the talk is talking about common risks to software security, specifically around APIs. This is based on a fairly recent report from OWASP on API security. And then we'll talk a bit about what can we do about it. What can we do day to day in our teams without huge budgets and remediation programs? What can we just do day to day to make things better and to avoid many of these common problems? My name is Eoin Woods. Pronounce it Owen. I know that's not necessarily obvious. I've been CTO at Endava for a number of years. Before that, I built software products for about 15 years. And I worked in capital markets companies, that's in finance, for a number of years as well. I've been trying to bridge security and development and bring the two worlds together for a very long time. I can only say how easier that has become in the last 5 to 10 years when many development teams now do see the need for software security, which is absolutely fantastic. In Endava, you've probably not heard of us. We are a mid-size, I guess you would say, software development company. We do all kinds of software development for a range of clients in many countries. It's about 7,500 people. So I've told you a little bit about me. Step one is I thought it'd be nice for you to tell me just a little bit about you. I'm going to switch on a poll. I'm just launching the poll now. And it says, who are you? Here you click one or more buttons that just tells us who you are. Just 30 seconds. You can see the votes coming in. Everybody? Brilliant, thank you. So I think you can see it in the polls system, but most of you are developers. Some of you are I think, also testers. And I've got one security engineer. Welcome. That's great. So what is the current state of API security? Sorry. Firstly, why does it matter? Security is important because we need dependable systems, and there are many aspects to dependability, as you all know. This isn't an audience I need to explain this to. But the reason dependability is a problem is because security people say we need systems that are reliable in the face of malice, mistakes, and mischance. Or to put it in everyday language, some people are bad, some people are careless, some people are just unlucky. And it's often the case in the security field that there's a great focus on the bad guys. There's actually security is just as important for ensuring that the unlucky people are sort of protected from themselves, if you like. And system security aims to mitigate all of those situations. Today's threat landscape can only be described as worrying. If you develop APIs today, and many APIs today are connected to the internet, it's a fairly worrying situation. One of the things that we've seen quite a lot in the last few years is internal applications are now being connected to the internet for totally understandable reasons. We've moved into the era when we used to connect systems to the internet. Now the internet is part of our system. It's just everyday part of what we do as software developers. And this is to be expected. But now, instead of being hidden away in our data centers where nobody even knew the API was there, now the APIs are on the internet and are often can be scanned for automatically by very large-scale automated scanning tools. And add to that the fact that today's APIs are typically quite easy to introspect, especially those that are exposed on the internet. If you've been doing software development as long as I have, you'll remember things like LU 6.2 on IBM mainframes, and you'll remember things like Sun RPC, the original XRPC, the original binary RPC protocols, all done in C and C++. Those APIs just sat there, and they expected exactly the right protocol to be communicated to them, and then they would call code and they would send the results back. There was no introspection. You either sent them the right stuff, or they sent back an error, or they crashed. Those were your options. Whereas today, of course, many web APIs have got introspection built into them. I mean, how many APIs today can you call the URL, put $JSON at the end, and you get back a Swagger block which tells you exactly how to call the API. So not only are the APIs on the internet, they're also quite easy to find out about. But the thing that really concerns me personally, and many people in the security field, is how attacks are being so-called weaponized. By this means, they're being made available, typically by the dark web, to people who would not be capable of exploiting those attacks themselves. What's happening is that people who, in I suppose only a few years ago, there were many possible attacks on systems, but actually you had to be quite skilled to perform many of them. So the number of actors who could do this worldwide was limited. Today, what these actors are doing now to make more money is they're packaging up these attacks in easy to use, SaaS, SaaS software as a service, or point and click packages that allow people to exploit known problems or exploit zero-day vulnerabilities, or to use to do well-known attack sequences on particular kinds of software with almost no skill at all. You simply need to find the right package, pay for it with Bitcoin, download it, and off you go. While this is maybe an admirable example of somebody monetizing their skills, it's pretty concerning, because it now means that a US college kid with some time on his hands and a few dollars can download an exploit kit and can suddenly become very dangerous, not really knowing what he or she is doing at all. It's democratized software violence, you could say. And the results of this are sort of obvious for many of us to see. The information is a beautiful website. If you've been to one of my talks before, you'll know I use this visualization quite a lot. I think it's really quite powerful. Is that what they do is they take data sets from many, many different places, not just security ones, and they visualize them. And the challenge for them is the visualization. And they show you how to visualize things in different ways, which is great. This particular data set is one that they have assembled to do with data breaches from 2005 onwards, and they update it occasionally. And they've used this sort of planetary metaphor for visualizing them. And you can see back in 2005, 2006, there weren't very many data breaches. By 2008, 2009, they were becoming more common, and there were a few moderately large ones. The US military, you might remember if you've been in security for a while, the US military, one of the first really, really embarrassing breaches from a government agency, where they lost a tremendous amount of private information about everyone who worked for, I think it was the US Army, in a data breach. But you can guess where this is going. There's a lot of white space on this slide. The white space is the good situation. The color is the problem. As you can see, from 2011 to 2015, there's the bubbles get bigger, meaning the impact, the scale of the breach is getting bigger, and you can see there are many more of them. There is less white space. And I think you can probably guess what's going to happen if we get to 2016. Sure enough, is that by 2016, you can see that there is really they're starting to struggle with their visualization metaphor, is that it's no longer working so well, because now they're having to scale it such you can't read the small ones. So this is the reality that we're facing. So in 2020, you can see, in fact, 2019 is probably worse. 2019 is almost entirely full, and the breaches are getting vast. So this is why all of us need to be taking API security pretty seriously. There is a tendency, though, for everyone involved in security, but especially app teams, to say, this is absolutely something that someone should be sorting out. What they mean is, somebody should be doing this, but not me. I mean, I'm too busy developing the application. And quite often you'll hear the statement that security is very important, and those infrastructure guys are working hard on it, and that should be fine. And there has been a tendency over the years to push the security problem to the infrastructure teams and say, oh, the infrastructure teams add security. I mean, again, for this audience, I don't really need to explain this. That's not a good way to go about achieving security. But just to be clear on that point, if you look at reports that are done on a fairly routine basis, I've just picked 3. There are many of these. Verizon run a data breach report. Verizon create a very thorough data breach report every year. Micro Focus occasionally do publish data analytics based on their Fortify on Demand product. Fortify is a static code scanner. We'll talk about it very briefly later, actually. That scans code for vulnerabilities. They've done analysis of and on demand is their SaaS version, so they've got the data. So they've done obviously anonymized analytics on that. And Forrester have simply run a survey. They've simply gone out to senior IT folks, their clients, I suppose, and said, I think you've had a breach. Could you tell us a bit about it? What is obvious here is that applications are a significant part of the mix. They're not perhaps the majority, but they're big enough that they're really significant. Verizon are finding that at least it's something like 25% of breaches are caused by, at least partly by applications. Micro Focus really, if you look at the bar chart there, really fascinating. 93%, I think they said, of applications that they scanned had a defect, a security vulnerability in the security feature. Now, it's just worth, before we write off those people as obviously not being very good at this, we just bear in mind, these are the people who are interested enough to do static scanning of their code, and very many people don't. So these are people who are thinking about security, and 93% of them manage to have some kind of problem in their security code. So you can see that, you know, people do make mistakes in this stuff all the time, which is why we use the tools, which is great. Hopefully none of those got into the wild. And then the Forrester survey, which obviously it's a little anecdotal, it's just asking opinions, but these senior, probably IT managers of various sorts, thought that about a third of the incidents that they had encountered or suffered themselves, a web app was the root cause, which, you know, this suggests that, while of course there are many people involved in security, the application development teams, we have our part to play. One other thing I realized actually when I was producing these slides was the term API today has almost got neutered to mean one very specific kind of thing. Because of course, APIs are as old as software, they're not a new thing. It's only in the last few years that you find APIs being discussed in The Economist, or my mum knows what an API is because she's read about it in you know, the Times or whatever. But of course, APIs are as old as software. I mean, it's any interface that allows one piece of software to call another. In this talk, we're really interested in network APIs. And even network APIs, as you all know, there are many sorts. You know, there are RPC type ones that go back, you know, decades and decades. There are remote invocation ones, the remote object ones. There's the REST style ones. There's GraphQL, which is, you know, a specialization of that very specifically for handling data sets. For this particular talk, we're going to talk really about REST style APIs. So the important thing is they're probably carried over HTTP. They're not a complicated binary format with stubs and skeletons. They're the sort of more adaptive and more, I suppose, standards-based APIs, and also, of course, the more introspectable and arguably the more exploitable. So I've got a second poll, just to make sure you're all still listening. It's kind of interesting, I think, just to find out what tech stack you all work on. I couldn't possibly cover them all, so I've done my best to just guess, really, who probably attends Accu and what stacks you might work on. So if you want to just all select as many as are relevant to you, which tech stacks do you mainly work on? Still answering? No, I think we're there. Are we just about there? Oh, 10 more seconds for anyone who's still wavering. Great, thank you. So the answers, I think you can see the poll actually, now I've closed it. But so most of you work on C and C++ applications as opposed to embedded. A few of you work in embedded. And then there's a sprinkling of people working on other stacks such as JVM, .NET, Python and JavaScript. So that's really useful, thank you. I will confess, I always have to fess up at ACCU. If you've seen my talks before, it's normally the first thing I say is, I did program in C and C++ but a very long time ago, but I've not done it for a very long time. And I'm really sorry. It's not that I don't like it. It's simply, that's the way my career took me. So I'm primarily working in JVM-based technologies. So a quick introduction, then let's just kind of talk a little bit about what we mean by software security. It's quite a big field. And then the OWASP organization, just for anyone who's not come across them, spend 2 minutes on this. Security is quite a big field. On the left-hand side, there's sort of application stuff. On the right-hand side, there's infrastructure stuff. And underpinning it all is operations, secure operations. So an awful lot of security experts, security engineers, security managers, CISOs, those kind of people, they come from the blue side. So they come from secure infrastructure design, you know, people like Cisco certified network architects, those kind of people, or they're experts in, you know, large-scale PaaS deployment and this kind of thing, maybe cloud infrastructure specialists. And also all the people who work on the actual tooling and day-to-day design, build, test, deploy of, you know, modern infrastructure environments. a lot of them come from that side. My interest and the interest of this talk is really a bit more on the left-hand side, which is how do we design applications so they will be secure, and how do we implement applications so that we will implement the design securely? There's no point designing it well if we don't build it well. This talk actually bleeds a little bit. Most of my talks are very firmly around the orange boxes. This one bleeds a little bit into the other areas just because, given the APIs, we're assuming here it's probably a public API we're dealing with. It bleeds a little bit into infrastructure and operation, but really not very much. This is very much a talk in the orange space. So, another poll. He's gone a bit quickly at this point. What sort of security work do you personally do? Just launch that poll now. Just 30 seconds on this. Oh, it's still going. Sorry, I was just about to close the poll. 10 seconds. Okay. Again, hopefully you can see that now. So a good range, actually, from security design through testing. Lots of people doing secure implementation and also doing infrastructure. One security engineer, welcome. And then people doing some other things too. That's great. So I've mentioned OWASP a couple of times without really explaining what on earth I mean by that strange term, just for people who haven't come across OWASP. I probably should have had a poll on that, who's heard of OWASP, but I'll quickly go over it anyway. OWASP stands for the Open Web Application Security Project. They're a big volunteer organization dedicated to application security. They started off completely looking at web applications. They started around about the late 90s, early 2000s in Silicon Valley, and they have spread around the world from there. Today, they're interested in almost all aspects of application security. They don't particularly look at infrastructure or secure operations or any other aspect. They're largely a volunteer organization. They largely operate in the virtual world online. And their reason for being, their mission, if you like, is they exist to improve the state of software security. And software security is the term that has emerged for application security in the last few years. So the security of software itself. They do research to find out the state of practice. They build tools. If you've heard of the ZAP, OWASP ZAP, the ZAP attack proxy, that's a well-known open source tool that penetration testers use. That's an OWASP product, if you like. They publish guidance, so quite strategic stuff, and also very detailed tactical stuff on how to avoid certain kinds of problems. And they also, in some cases, create standards. So they're a very useful organization doing an awful lot of good work. They also run face-to-face chapters. So anywhere you are in the world, almost, there's probably an OWASP chapter not very far from you. I checked, there've been a few open even since last time I looked 18 months ago. I mean, in the UK now, there must be like 15 chapters. They're all over the country, from Dorset in the south up to, I think, there's OWASP Scotland, which I think is based in Edinburgh. So there are OWASP chapters almost everywhere. And they're most famous for the so-called OWASP Top 10. These are projects that they run in the research area, really. They do research into what are the 10 most dangerous risks that people face in the web app security area, in the mobile security area, and more recently, the API security area. Most people have only ever heard of the web app one. In fact, most people, an awful lot of people in the industry have heard of the OWASP Top 10, even if they've never read it. And so you'll often hear people referring and passing to, oh, we're aware of the OWASP Top 10. Actually, that's quite ambiguous. What they nearly always mean is the OWASP web app Top 10. And normally when they say we're aware of the web app, the OWASP Top 10, what they mean is, I've heard the term and I've never read it, so I've got no idea what it contains in my slightly cynical view, having talked to many people about it. But there are actually 3 of them. I have done a talk at ACCU before on the web app ones, and we're going to talk today about the API ones. And I'm totally unqualified to talk about the mobile ones, so I don't have a talk on that. There's a couple of other organizations it's worth just being aware of. Very, very different. The MITRE Corporation, you're probably aware of, they're a US, largely government-funded organization, but they are a private company. They do a lot of work in the defense area, so they're not always everyone's favorite company, but they are important in the security realm, partly because they maintain two of the canonical lists of problems with security, the common vulnerabilities and exposures, the CVE list, and the common weaknesses enumeration, the CWE. They're all freely available on MITRE's website. So, I mean, those are things that security people do use quite a lot. They're worth being aware of. Particular people, I'm sure you've heard it, people talk about which CVE vulnerability are you talking about, and there'll be a CVE number. And if you actually want to know what the detail is, as in how it was found and so on, cv.mitre.org is where you would go to find that out. Another totally different organization, Safecode. They, in a sense, are a little bit like OWASP. Their reason for being is to improve the state of software security, same as OWASP. They're a little different in that they are a consortium mainly of large product vendors who've got large and very sophisticated security engineering groups. They wanted to pool their knowledge, partly for their own good, but also for the rest of the industry, particularly their customers, to improve software security. What they do is they've published a very big, comprehensive book, really, an ebook called Fundamental Practices for Secure Software Development, which tries to distill accepted practice across big industry players such as Adobe and Google and many others I can't remember. There's about 8 or so, I think what they call charter members. That's members who were invited to join, and they put significant time and effort into it. And then any organization actually can apply to join Safecode, and they get a certain amount of influence over it. And I think they get early access to materials and stuff, but they charge them fees. The really important thing, though, is that none of the Safecode deliverables are charged for. So that guide and all of it, and they produce training material, they produce developer guides, it's all free of charge. And that's why I mentioned it. It's very definitive stuff. It's written by people who really, really know about software security. And by design, it's all given away free so that they hope people will use it. There are many other organizations, but those are just two I think it's worth being aware of, is that MITRE for the CVE list in particular, and Safecode because there's a tremendous amount of useful material that they give away completely free of charge. So, moving on to the top 10 security risks then. As I mentioned, OWASP is a volunteer organisation, and it would be fair to say that most of what they do is done through volunteers. This is another volunteer project, just like the Web App Top 10. It was written by 3 authors with only about 35 people contributing. Most of their projects are significantly larger than that. This is quite new, it only happened in 2019. And so it's quite a lot less mature than the Web App Top 10 that I think was first published in 2003, and it's had about 4 versions. I can't remember off the top of my head, but I think it's 4. I should know really, so I'm going to talk on that. What they did was they did an analysis of public data sets. They then did a survey of pen test practitioners, and then they produced a sort of draft top 10 list, and then they did expert review to kind of refine it and produce the final one. I think it would be fair to say that they still have some way to go to get full conceptual consistency and coherence in their list. There is a certain amount of overlap between different items in the list, and there's also some things missing which I think are a little bit surprising. That's not to say it's not useful. It's simply not as mature as some of the other projects. I mean, the first versions I remember of the web app list were, much less coherent and mature than the one that is there today. So it's just going to take some time for them to get there, but it's a very good starting point. Next time around, whenever they do the next one, they plan to do a public call for data and to make it a more quantitatively driven exercise, more sort of data analytics rather than opinion, which is how the Web App Top 10 has matured. I'm not going to read them out, but these are the 10 we're going to look at in the next 20 minutes or so. The thing that's interesting about them is some of them, the ones I've highlighted, are very closely related to similar items in the Web App Top 10, but they're slightly different because they're in an API context. And there are also some surprising omissions, in my view anyway. Number 9, I think, in the Web App Top 10 is vulnerable components. Many of us today import large amounts of open source into our projects, and we frequently have no way of checking them for software vulnerabilities. We have to rely on self-reporting, where we rely on other people finding them, and we rely on staying up to date with what's going on in those projects, which is frankly a problem. That's interesting it didn't make this list. I mean, I think you should always think about it anyway, but clearly the experts who looked at this obviously felt that actually these things were actually even more important than vulnerable components. It'd be interesting to see next time they produce the list if that stays the same. So number 1 then, let's get into the list. So number one, broken object level authorization. This may be quite familiar to you because it's in the web app as well. The problem is that nearly all APIs authenticate reasonably well. Once they've authenticated, they often don't fully authorize access to all of the objects that they're giving access to correctly. To make matters slightly worse than that, the object keys, the identifiers they're using, are often eminently guessable if you've got one to start with. Because how do they allocate them? Well, they often allocate them in monotonically increasing order, roughly, rather than them being randomly selected and so hard to guess. So, you know, a completely fictional example, but you get a report from this provider. What would happen if you change the number? The number presumably is the client ID. What would happen if you change the number? So you're authenticated, but are they checking that you're authorized to access that specific item from the system? Well, it turns, hopefully, yes, of course, if you change the number, you'd get an error back, a 4 or 5 not authorized or something like that. It turns out that actually in pen testers' experience and many bug bounty programs, many APIs don't do this consistently and reliability. It's obviously we need to enforce object authorization on every request. The other problem can be is that the API namespace, if you like, is not always well structured and very regular. And so developers sometimes might just be confused by the structure of the API and they're not quite sure what's meant to be secured and what isn't. And the other thing, of course, is functionally test this. This is not even security testing, this is straightforward functional testing. And don't use IDs which are, when you've got one, you can guess all the others. Use long random numbers if you possibly can. Possibly just in the API, perhaps not within the system, but making sure that you don't expose easy to guess object IDs through the API. A good example of this is Parler. You may remember Parler. Parler was well, I believe it's been reborn, but it was shut down for a while. It was a platform, a bit like Facebook, but apparently for free speech in North America. Free speech, but not free of responsibility, not free of implications, as one security wag put it. Parler was interesting because soon after it was announced that Parler was shutting down, but after the riots at the Capitol, a security researcher, attacker, whoever she is, it's a Dutch woman, who goes by the charming Twitter handle of Donkendi. She organised the extract of nearly all the data from the Parler platform. How could that possibly be possible? Well, it was caused because Parler authorised you, but it turns out that they authenticated you, so they knew who you were on the platform. It turns out that actually the authorization was really done in the app, not on the servers. So this allowed Donkendi and her helpers and supporters to simply register for Parler IDs and then extract all the data from the parler.com servers. In fact, some of the Parler data, there's some confusion there because Parler's no longer there to poke. You can't go and test it yourself. But it turns out that there is some confusion because there are various scripts in various GitHub repos, which you will find if you follow some of those links down there, that show that actually some Parler data, it seems, you could retrieve without even authenticating. And as far as I can see by looking at the scripts, what Parler's double level mistake was, they authenticated you when you came in through the app. And to call the API, you had to be authenticated, but the authorization was done in the app. Meaning if you went directly to the API and were authenticated, you could extract anything. The other thing was that they used very guessable keys. So having got one ID, you simply added one, and what do you know? You could extract all things of that type. The other problem seems to have been that some of the content, such as video, which was linked from the main content, was stored sort of alongside the main Parler servers, and you could retrieve that without even authentication if you had the URL. They seem to have relied on the fact that the URL was a long, complex random number. It was some kind of object ID, S3 ID or something. They seem to have relied on that rather too heavily, so that actually if you could retrieve the post that had the link to it, then you could just simply retrieve the video. And they did manage to retrieve nearly everything that was in the Parler platform. Number two is another kind of broken access control, but this is user authentication. There's a whole range of possible problems here rather than one, but it's things like, does your system allow credential stuffing? So credential stuffing is where you've got a huge set of usernames and passwords, and you just try them all in order. You've got like a million of them, you just try them. will your system spot the fact that there have been 1,000 login attempts for logins that are not in the system? Because if not, you are potentially open to a credential stuffing attack. The other common source of attack, of course, is a brute force credential attack. And that's where rather than trying thousands of random usernames for one username, you try 1 million common passwords on the basis that many people do use very common passwords. There's also occasionally people make mistakes and they use API parameters to pass in authentication information, such as API keys, which obviously that can just be intercepted and extracted and then used. And sometimes people are using really, really solid security technologies like JWT, JavaScript Web Tokens, for which are bearer tokens that can prove who you are and what you're authorized to do, but actually they're not validated properly. So somebody can forge a JWT token, and the system naively just pulls the claims out of it and honors them. That's more common than I think anyone in the security world would like to admit. And also, of course, some security technology can be quite complicated, so mistakes in protocol implementation are easy to do. This is not tremendously interesting from an examples perspective, but we'll see in example 10 that this is part of a bigger attack. And the mitigations are to use multi-factor authentication in case people do break in with a guest password. All of your login and credential recovery stuff, you should have controls around them so that there's rate limiting, password rules, lockout periods, people get failures, captures, and so on. Use existing authentication mechanisms. There's a lot of mistakes to make in authentication, so not doing it yourself. If you do use third-party technology, which actually not generally support, it's normally the right thing to do, just be aware of how it works. A lot of it is reasonably complicated and subtle, and like with JWT, if you don't know how to use it, you can inadvertently use exactly the right thing, but in the wrong way. Obviously, implementation needs to be done carefully, and you need to get experts to review it. And functional penetration testing is really important to just check this stuff out. Number 3 is excessive data exposure. What this means is that when you call an API, you're expecting a particular piece of information back so that you can perform whatever action you're trying to perform. Many APIs, a lot of pen testers note this when they're exploring APIs, they return way more information than seems to be actually needed to perform the action that the client is trying to perform. And often client-side filtering in apps and web pages hides this from end users. The problem, of course, is that if you've got a piece of software calling the API, they've got all that data. And the reason is perfectly understandable in most cases. An API developer doesn't want to be fine-tuning the API data definitions every couple of days. So they somebody says, I need to get the basic information for the user account. They go, well, I'll just put in all the information for the user account because they might use it anyway. And it's not like they'll show it to the end user, they'll just filter it out. A perfectly rational thought process. It's just when you think one more step ahead, you think, oh, hang on a minute. I don't really know who the client is. As we'll see later, I mean, that's a key tactic, isn't it? Not trusting the client. And one of the problems with this is no automated tool is ever going to pick this up for you because the automated tools don't know your data model. A real example of this was Facebook Marketplace in 2019. And a penetration testing company, 7 Elements, picked this up and wrote it up very nicely on one of the guys' blogs. What was happening here was that in Marketplace, you can see from the user interface on the left-hand side, they've got a cute little map widget that tries to show you the rough area that the goods are located in. So I guess you can sort of see, is it close to your home or not? Is it somewhere that you can get to? Is it somewhere you visit regularly? Sounds like a great feature. As long as you don't tell them exactly where the goods are, because then you're sort of helping someone create a burglary shopping list, as this person put it. And actually, unfortunately, that's exactly what was happening. The way that this feature worked was that the Facebook servers returned an absolutely precise location of where they thought the goods were. In other words, the address of the seller, because the seller had to be registered so that they knew exactly who they were. So they had a home address for them. So it gave their exact home address location. And then it was the client kind of went, well, that would be silly to put that on the screen. What I'll do is I'll ask a geoplot library to start at that point and then draw a circle around it. And presumably, I'm hoping they also offset it a bit so it wasn't even obvious where the center was. The problem was if you called it through an API, you could get the exact locations of the goods. So super expensive mountain bike, retrieve all the information. Now you know where to go to steal a mountain bike. in general, clearly the main mitigation is just remember that you can't trust who your clients are in those cases. And this is another example of the need to know principle. Let's give people the information that they actually need, as opposed to trying to be helpful and give them a load of perhaps quite sensitive information, which they don't need right now, but might come in handy someday. Related part of that, which is actually related to one of the other number 6, I think. Number 6 mass assignment is don't generally just return a serialized form of an internal type, because obviously even if that's okay today, somebody could add sensitive information to that internal type, which just gets blindly serialized and returned to the client sometime in the future. So use API types, and also just make sure people have got awareness of where the really sensitive information is in the system, like PII and card data. And make sure that any time that's picked up and returned, that's reviewed. That's absolutely the right thing to do. Number 4 is resources and rate limiting. And this is because classical denial of service attacks use network protocols. So this is why it's the infrastructure guy's problem, right? It's a SYN flood. I mean, every application developer's heard of a SYN flood. None of them wants to have anything to do with it, because that's an infrastructure thing. So our firewall can sort that out. And they're quite right. I mean, that's an infrastructure concern. APIs themselves, though, are highly vulnerable to overload attacks, typically exacerbated by people passing in daft parameter values, which cause the API to behave in an unexpected way. The 2 dimensions are how many parallel requests can you make to the API at once? And the second thing is how big a thing can you ask the API to do each time? So the ways that we can mitigate this would be rate limit at the API level, only allow so many requests in. Rate limit at a particular session or user level. The attacker is probably going to be using a limited number of sessions. Put hard limits on parameter sizes. I mean, I think that's a key one, is that, never allow n to be, a uint 32. And also in the runtime environment, this is why this crosses over slightly into operation, you can put hard runtime limits on memory, CPU, file descriptors, and so on. Especially in the world of containers, this is one, straightforward to do, and secondly, really important, so that no one container is ever allowed to explode in size or to burn massive amounts of CPU. That just shouldn't happen in the API. So put the limits on each container that you've got, and then that will help to mitigate this risk. So, again, completely fictional example. You extract something, there's a mild attempt at obfuscation of the fact that the name is actually a wildcard search, and you ask it to return anything it's got up to this massive size. Hopefully, this immediately gets thrown back with an invalid parameters error, because that number is far too big. Again, turns out penetration testers will tell you it's surprisingly uncommon for that to be the case, which is obviously unfortunate. What could happen in this case would be it tries to extract everything from the database, be it NoSQL or SQL, and tries to assemble a massive result set in memory, so crippling the API. And so if you did this 40 times in parallel, you could cause problems in both the database and in your middle tier. And number 5, broken function level authorization. We're back to authentication and authorization. There are quite a few of these. This is, excuse me, not checking that the specific function you're performing is authorized for the specific principle, security principle that is, that is trying to perform it. So it's incomplete or incorrect one. My experience with this, the report makes this sound as if people are just not doing any authorization at all, which I don't think I've ever seen that, to be fair. I think it's that people do authorization, but it's quite a complicated thing, and it's easy to leave a hole in it, or to have an implication in your configuration you're unclear about, or to extend something and not realize the implications. And so maybe you've got a complex security model, and I've worked on a few of those over the years, where you've ended up with all these special cases in the security model where if somebody said, can this principle definitely access this function? As a human being, you'd be struggling to answer the question because there are so many special cases. And so that means that it's quite hard to know what right is, what correct is. It can be just the complexity of the application, or it can be, in fact, you're using a third-party component, a third-party authorization system that's actually quite complicated, and that can make it difficult to know if you're right or wrong. Real example of this was found, again, by a penetration tester. This is via bug bounty. That web page down at the bottom is a list. That's a write-up from somebody reporting on a bug bounty penetration tester's experience with New Relic. To be fair to New Relic, we always feel slightly guilty criticising these firms. New Relic's problem is only out in the public domain because they were happy to create a public bug bounty on Xhacker, pay people to find bugs, and to have the discussions in public. Now, so that means we can see New Relic's problems. To suggest that their competition don't have the same problems is clearly very unlikely. It's just that they're prepared to share those with us. But they did have a lot of function level authorization problems when they ran their first bug bounties. It turns out that the way their API worked was that you used a post with a particular REST URL to create a thing called a filter set. And that's a filter set generally created by administrators, and they used to filter the New Relic dynamic monitoring API. And you passed in a parameter block, a JSON block, configuring a new filter set. Turned out that perhaps they hadn't thought about other HTTP verbs, because it turns out that calling delete on exactly the same URL deleted the filter set, but without any. Sorry, I should have said the create was correct, had a correct authorization check. So you had to be an administrator to do this, and that's exactly the way it's meant to work. It turns out that deleting it, you could use the same URL with the delete verb, and there was no check who you were whatsoever. It would just delete it. So it was, obviously New Relic didn't explain why the mistake was made. My suspicion is that actually deleting it didn't use the delete verb. They used post with some different parameters, and that nobody had thought how delete worked, that perhaps a framework was interpreting delete for them, or a developer just decided to add delete because they thought, oh, this REST API is incomplete, something like that. How it happened doesn't really matter. The point was that calling delete with the URL just removed it, and there was no authorization check at all. Obviously, it's fixed now because it was found in the bug bounty. And so the mitigations are, we're back again to simplicity, if you understand that you can secure it. Making sure the sensitive stuff is understood so that there's more attention around those. Authorization is very functionally testable. This is not really complicated pen test stuff in most cases. I mean, there is definitely a role for pen testing, but that's not in any way critical to the basics. Again, understanding security technology. Again, don't invent your own security technology. That's a repeating theme. And again, pen testers will always tell you it's amazing how many bits of technology, when they hit problems or there's configuration ambiguity, do not default to no access. A lot of it defaults to access. So always default to no access. So time for another poll. Check you're all still awake. So question 4, of those 5 initial problems, which of those do you think would keep you awake at night the most? Now we're going to have a break for 5 minutes. Just let you get up, wander around. Very quick coffee, if you can make a coffee in 5 minutes, just to give you a chance to have a little break and focus away from the screen. So I will start timer. There you go. And I will see you again in 5 minutes. Please answer the question during the 5 minutes. Thank you. Okay, welcome back. Let me just close the poll. So I think you can see it, which is, resources and rate limiting being one that is a major concern. I'm with you on that, because it's something that it's very easy to just kind of get out of your consciousness, because it's almost not a security thing, isn't it? I mean, it's resources and rate limiting, that sort of infrastructure. But actually, no, I mean, there's a lot of implications for applications too. So let's see what the second set of the 10 are. Just move the jumping poll out of the way. Number 6 is mass assignment. We alluded to this one earlier when we talked about not passing too much information around. Different fields in a data entity in the system often have different sensitivities. I mean, whether somebody's an admin user is a lot more sensitive than their title, for example. Well, it depends what you mean by sensitive, but in terms of what they can change, it's much more sensitive. And we often use libraries to bind data elements to and from types, which are API parameter sets typically. So in JavaScript, you might use JSON.parse to parse a JSON string into a Java object, JavaScript object, and back again. If you're a Java person, you might be using Jackson. As I said, sorry, I'm not a C++. I know there are such libraries in C++, but I have no credibility talking about them, so I'll just tell you about ones I have used. So Jackson is the big one in the Java world. It's a JSON parsing library, and it's got a really nice kind of mapping system in it, which will map the stuff from the JSON block into a new instance of that type of trade. The problem, of course, being we said you can't trust a client. The client can add rogue fields in. A real situation where this happened is a company called Harbour.io. They unfortunately are very public in their mission statement, which is to be the trusted cloud native repository for Kubernetes, which is fine, except that their product contained a really significant privilege escalation vulnerability, which was found by a penetration tester at Palo Alto Networks, not by Harbour themselves. It was a classic thing where to create or change a user, you posted a JSON block to their /API/users endpoint. All fine so far. Problem is that it didn't check what was coming in. It was only expecting information about the user, which the user could change. Turns out that you could that the penetration tester had a look at their source code, spotted this has admin role, and just thought to himself, I wonder. Sure enough, he could post adding that field to the JSON block, and the user magically got admin role. Oh dear. And that was a JSON mass assignment operation. The guy on his blog actually pinpoints the line of code, and obviously it's fixed now, but it was very like JSON.parse. It was a very similar kind of utility. Obviously, what they should have done was, it's almost trivial example of whitelisting, where we want to have a little filter filter function which allows you to just knock out anything you're not expecting, and then it's very easy for people to use. They can whitelist the fields that they're happy with, call it, and be sure that afterwards, having started with a record with a third field agent notes that we're not expecting, because the agent notes are only updated inside the system. And actually, if you're interested, if you decode that, you'll find that there's some code lurking in there that we can put it through our filter, and obviously we come out with a sanitized object. The key thing is that most developers rely on automatic data binding libraries. Why wouldn't you, in a sense? Because it's just such tedious code to write, and people make a load of mistakes with it. So a binding library is great. It's just that it's two things, really. If you're binding to and from the API types, you're a lot safer. And secondly, be aware of people changing the types, so that look for data binding libraries that allow you to use whitelists. Number 7 is the eternal security problem, misconfiguration. A whole raft of possible problems rather than a single type. Not getting your security patches in, more infrastructure than us, but what did we say about software components? Are all of your open source components up to date with no security vulnerabilities? It's very hard to know. Incorrect configuration of authorization or perhaps authentication mechanisms. Having unnecessary features enabled, perhaps you are unwittingly exposing network interfaces because of a third-party piece of software that you've imported. Really common with complex open source libraries. Do they, for example, have a management port which they open automatically without telling you, which is now sitting as a potential vulnerability point on your application? Security enforcement being incorrect. Like, you've got an architectural style that says we use TLS everywhere, and that's all great, but actually it's not always done consistently. And exposing sensitive information. Pen testers love to talk about this one, that whenever they go to Java-based web systems, if they can force them to stack trace, then particularly the Tomcat server, its default behavior is to display the stack trace. Stack trace including all of the detailed information about exactly what software is running, and you've now got some idea of what their internal software structure is too. And mitigations here is you pretty well got to test for it. It's very hard to spot misconfigurations without testing the result, rather than actually trying to test the configuration code itself. Use as much automation in that as possible, because that will bring you consistency and avoid human error. You obviously use expert review. Some of the stuff's quite complicated, and handle errors carefully. I've got 2 examples of this one because it's so common. Algolia search has become a little bit infamous. Not to be fair that there are necessarily real security problems in Algolia. Algolia is an enterprise search technology that is shipped. It's a server and a library. You embed it into your applications. It's quite popular. Seems to be a good product. A number of penetration testers, though, have noticed that when they went to test systems that had Algolia in them, by using the Algolia endpoints, they could seemingly get privileged access into the system through Algolia, which was a bit strange. Turns out that Algolia uses an API key to authorize access to it, which is, as a URL parameters, arguably not the most secure way anyway, but let's leave that on one side. They use an API key. However, the API key identifies a security principle and hence a set of authorizations. It turns out, though, that you should only ever be calling Algolia using the client API key in normal situations. And that has a very limited number of privileges. It's got one, search. That's all it's allowed to do is search. And that's exactly what you'd expect. Turns out that many people have accidentally configured their Algolia implementations to use the admin API key to do the searching. And that means that if you can get something forced into the URL or into the post block, you can also add things to Algolia, edit its settings, list its indexes, and so on, all of which are potential security problems. And the reason for this is not actually the software, slightly unusually, it's the documentation. It turns out that when you go to the Algolia documentation site, there's lots of handy snippets of code to copy and paste into your code. Well, I've never been that keen on copying and pasting to start with, but leave my biases aside. The problem is that these, if you're logged into the Algolia site and it recognizes you, it uses your admin API key in all of these code snippets. So people could obviously not really think you've gone, oh, I'll take that bit of code and just use it over here. But it turns out they're using the admin API key right across their enterprise application. So it's a really serious misconfiguration. Second one is Capital One. They had a major data breach, you may remember, and I'm not poking fun at Capital One. I have, knowing people there, I have immense respect for the Capital One team, but even Capital One were caught out. To simplify it slightly, I mean, Krebs, security researcher, has done quite a lot of write-up. You'll find lots of speculation about the Capital One breach all over the internet, but it seems that basically this is how it happened. An attacker got access to a reverse proxy into one of their EC2 VMs. They were using mod security as their reverse proxy, or application firewall. From the EC2 VM, they were able to use Amazon's IAM feature to swap identities, and from that, they were able to then access an S3 bucket. In the S3 bucket, unfortunately, was lots of person identifying information, which they were able to exfiltrate back along their path in. I'm not going to do the whole thing here, but what's kind of interesting here is that the problem, the root problem, if you like, was a mod security implementation. There was a problem in the text configuration file, which allowed somebody to get access to it into one of their EC2 VMs, which actually shouldn't have been possible. Unfortunately, it was. Again, it's a security misconfiguration. Before we get too superior about Capital One, bear in mind that that's the default mod security configuration. I'm cheating slightly. I've taken out the comments so I could fit it on the screen. But I don't know if you feel you could look at that and change it really confidently. I couldn't. I sort of know conceptually what most of it means. I wouldn't be confident in changing that and be sure that I knew what all of the side effects of what I was doing. And I think sometimes the security technology industry does not help itself. They create products that are complicated and sophisticated with configuration files that are positively human hostile. They require a high degree of specialization and knowledge to change themselves. Number 8 is injection. It's our old friend from the web app top 10 all over again. This is the vulnerability type that keeps on giving. It is, of course, dangerous in APIs as well as in web apps, because anything that can be interpreted can be injected. Database query parameters, command line arguments that are then used to create command line strings, configuration items that are parsed and processed. The way around this, of course, is relatively straightforward, although it's quite rare you actually see it in systems. You need to make sure that you check, validate everything that's coming in and reject parameters that look suspicious or have got strange lengths, strange characters in them, strange sequences, and then try and avoid passing data directly into an interpreter. Try and wrap that in something that's going to control how that data is used. So in this example, for example, ISAPI is the OWASP Java sort of security library, helps you build secure Java applications. In this case, it's using the validator module to make sure that the input parameters are valid HTTP parameter value. So it will throw out maximum length 12. So it'll throw out excessive length. It'll throw out dangerous ones that contain dangerous sequences. It'll throw out ones that contain strange control characters and so on. That would just raise an exception. So we'll just stop it at that point. And then the query, you'll notice that I'm not creating my own query string. This is the key thing. I'm using a prepared statement. So the database has to pre-compile the query, so it knows it's syntactically valid, and you can't just go minus minus and start adding things on the end. Is that it's actually, the database is actually inserting a value into a parameter inside the database. It's not creating the query stream. So we need to validate and standardize data entering and leaving the system. Use a validation library if we possibly can, because that makes the easy thing the right thing. Use APIs rather than interpreters. Interpreters, as we all know, are just dangerous. Sanity check your payloads. And if you can possibly do it, I know this is not always easy, but strongly type API interfaces. An awful lot of APIs today are trying to stress flexibility, and so they're not much more than a verb and then a bag, a map instead of name value pairs. I get it. And name value pairs are always strings. I understand why people do it. It does increase flexibility, but it does make it tremendously harder to spot security problems. Number 9 is unique to this top 10. It's not in the other two, and it's of quite a different sort. It's improper asset management, which is a grand term for not knowing where your stuff is. Many application estates today are not well understood. Old applications can run for years with very little attention, and they will contain vulnerabilities in their own software components. That's almost inevitable because they haven't been updated. They're often skipped during remediation work because there's only so much money, only so much time. They may have accidental or maybe even deliberate vulnerabilities built into them themselves in their own code, especially if they're old. And if they're compromised, they may not be noticed. So actually, they can become a jumping off point for an entire attack on your network because nobody's really monitoring them very carefully because they're just an old application. It's only processing a little bit of workload and no one cares very much about it. They can be a real security black hole. Even important applications, though, which you're maintaining actively and they're core to your business, can have old neglected features if they're more than a few years old. Perhaps old data interfaces left in place because you need backwards compatibility. You couldn't take them out. Unsupported open source components. Have you kept all the open source up to date? That can be quite difficult. Often there's a breaking change needed to adopt the secure version. And sometimes you end up keeping insecure mechanisms like plain old FTP because you're communicating with some old legacy package and it's only got plain old FTP. There really isn't a better option. So even an application you as loved and actively looked after can have problems in it which people may not be that aware of. And even a brand new application can introduce a problem. What are microservices? There are an awful lot of network connected moving parts. Every network interface being a potential vulnerability point. Cloud allows people to move much faster and deploy their own stuff. That's generally a really good thing. I'm a great advocate of DevOps with William Darver and beyond, and I think integrated teams doing all this themselves is the right thing to do. But where you don't have enough infrastructure knowledge, perhaps people are deploying the infrastructure really insecurely. Maybe they don't have the knowledge to do it really securely. And the rate of change in modern application states, where people are deploying maybe every day, the rate of change is so fast that keeping track of it is in the old-fashioned way, using software asset catalog. It just doesn't work anymore because nobody's going to put that much time into it. So you probably need an automated solution, which again takes time and effort to build. This is based on a real example I worked on. I've obviously sanitized it a bit, but this system started off on a monolithic core, and in the old days, to start with, it had a SOAP HTTP API. It was some years old. That was quite trendy when they started. And then somebody decided they wanted an asynchronous API, so they built them an MQ message queuing based interface with largely the same interface as the SOAP, still XML based. And that lasted for some years. And then, of course, the application was successful, so they continued maintaining it. And they decided to build a JSON over JMS asynchronous interface because the XML was aging and it was very highly used because there's this sort of high volume interface which other systems used. But also people were also using the HTTP interface, and they started saying, well, we're phasing SOAP out. Well, this team was going, well, we don't want to work with SOAP either. So they built a REST API. And then, of course, in the modern fashion, they built a couple of microservices, the REST APIs. And where do you think they spent most of their time and attention looking? Well, of course, they spent most of their time and attention looking at the bottom, at the modern interfaces. Those old interfaces are yesterday's legacy, but they're also potentially today's security vulnerability. And it's because the asset as a whole is quite complex, and we focus on certain parts but not others. And the other problem with asset management is scale. In most big organizations, you have thousands of applications, thousands of servers, thousands of services, message queues, databases, and so on. And it's all changing all the time. I think that's because they're a real organization. what this means is that it's tremendously difficult to keep track of what's going on. And there aren't any, once you've lost control of what is running where and what state it's in, I'm sorry, there are no easy mitigations. It's easy to say, but avoiding being there is really the most cost-effective way to do it. I know that sounds trite, and I know that it's very hard to do because nobody will ever value this stuff up front. But the more you can do to put the building blocks in place to manage what's in your state, the better position you'll be in. Network scanning can be useful to find things. At least you find ports that are open. That's obviously one dimension of the problem. And once you've found them, you've really got to invest in modernization. You've got to improve the security in place, or you've got to shut them down. Those are really the only three options you've got. And today, wherever possible, we should be automating our inventory maintenance. And the last one, number 10. Breathe deeply, you're nearly there. Number 10 is insufficient login monitoring. This is inherited directly from the web app top 10. It's much the same one because it's a constant problem in secure systems. Login monitoring very rarely comes for free in web apps or in APIs. And often it gets forgotten or deprioritized. People know they need logging, but they'll sort of get back to it, or they're doing some logging, but they're not doing enough logging to be sure what happened, or they're logging, but they're not keeping logs safe, so they're not acting as an audit trail, and. The problem is, if login monitoring is not good, it's very hard to detect and respond to suspicious activity. So to give you a fictional example, a friend of mine told me, suppose an API key is compromised, and it's thought to have been compromised on a Sunday afternoon. It's not really understood that it's been compromised until Tuesday morning. You can revoke it at that point, obviously. That immediate risk is gone. Could you tell what has been done with that API key from Sunday afternoon to Tuesday morning? That's a fairly big requirement, isn't it? I mean, to know everything it's done. Hopefully, you've got logs, they're running off into files that have being archived in the central system, your CloudWatch or your Splunk logs or whatever, and you can simply type in the API key and get it all. But there's an awful lot of systems that actually that's not true. That's why the prevalence of this one is 3, meaning it's sort of everywhere. It's quite rare to find a system that's got really good security. This is a completely generic example, but the reason I didn't use a real one is because there's so many to choose from. Almost every data exfiltration using web apps works this way. Bad person uses an automated credential stuffing attack. Do you remember I talked about this under number 2, broken user authorization, authentication? This is an example where it's very, very common they use a credential stuffing attack to get into a web app. And that gives them the ability to then jump on doing things. They then have access into the web app so they can use the browser as an attack platform. Remember, if you came to the web app talk, we discussed you could not design a better attack platform than a modern browser with the dev tools. I mean, it's basically an entire programmable environment optimized for launching attacks. They then get database access using an injection attack by kind of reaching behind the user interface in JavaScript, calling it directly. And then once they're in, they then exfiltrate data and store it. It's easy to say. I realize this isn't always easy to actually do, but actually think about it. Monitoring could have alerted the owners of this system and all these other systems to all 3 parts of this. There was very strange login behavior, which clearly wasn't picked up. There was an excessive database result set that didn't get terminated. And there was a very strange large outbound transfer, which again didn't get stopped. I mean, the right monitoring and logging can firstly be useful afterwards, but even during it can actually help you to respond. So the mitigation, it's all very well known. I know you've all seen this before. You need to log sensitive events, authentication activity, access failures, validation failures, especially the failures. Keeping logs accessible but secure, so they can't be simply overwritten. Using SEIM type systems, security event and something monitoring systems, to aggregate logs from different sources, because that keeps them central and safe and allows analytics to be run on them. Typically, SEIM systems come with analytics for logs built in. The other thing is build awareness of what normal looks like in your system using your logs, and then create dashboards to spot what's different. For example, if you got 15 login failures in a minute, would that be odd? I don't know. And I mean, if you don't know what your normal login failure rate, you don't know for your system. Whereas if you can build an awareness of what normal is, if you suddenly get 45 login failures in a minute, you know that's abnormal and you go and look at it. Whereas if you get, 16, you probably don't. Whereas if actually you don't know that figure of 15, You don't, 45 might be just perfectly normal. You just don't know. So building an awareness of normal and spotting deviations from normal is a really valuable practice. So, quick poll, check everyone's still awake. Which of the second 5 security problems do you think will be a problem, is most likely, sorry, to be a problem in systems you work on? What would keep you awake at night out of those 5? Okay, I think the results are in. Thank you very much. So hopefully you can see the poll now. What's really interesting is actually injection was 0 until the last couple of seconds. That's really interesting. And from that, I'm looking at that and going, you're a really security aware audience. You've probably got injection under control. And the fact that you don't think mass assignment is a problem also suggests that you're aware of the kind of risks that most API developers actually aren't aware of, which is a really good sign. I'm not terribly surprised that you've picked security misconfiguration, improper asset management, and insufficient logging, because those are actually just hard problems. It doesn't matter how security aware your teams are, they're hard problems to start. So that's very helpful. Made me feel much better. Well done. We're not actually going to have a break, apologies. We're going to just continue on now. So I'm not quite as far as I was expecting. So the vulnerability types, just to kind of classify them in the Woods taxonomy, they're basically injection problems, they're validation problems, they're mistakes in implementation, and there are problems with the environment the API is running in. Those are the kind of broad buckets that I find it quite useful to kind of think about these things in. So how would we actually go about improving software security? Let's think about what teams can do for themselves rather than being part of some great corporate program, which I'm sure is a great thing, but actually that's 5 years and no one's quite sure what it actually achieves. What can the team do itself? Well, the first thing is the entire team can become security aware. Unfortunately, in parallel to this session, one of the best ways I know of doing that is running at this conference. Charles Weir and Ingolf Becker are running their security awareness workshop, which is from their Developer Security Essentials material. It's developersecurityessentials.info, or .org, I think is their site. They've got a workshop specially designed that actually non-security specialists run it with teams to just get teams thinking about security in their own context. And it's a really useful way of raising security awareness right across the team. Second thing is bringing security into the design process. Most competent teams are great at design, but they don't necessarily have security as a first-class concern. So do they have, they've got requirements, do they have security requirements? And have they thought about them? Validate them. Do they do threat modeling? So in other words, that's the pencil and paper exercise to think through the implications of those, of the threats your system faces. Is there explicit security design? Are you designing the security mechanisms to meet your threats? When you're building, are you building with an eye to security? I know there's a lot of concerns. This is only one. Security people always act as if it's the only thing that matters, which is ridiculous. Actually, you've got to have the right product to make it worth securing, but there needs to be some focus on security through the whole thing. So, is there thought about security during the design process? Sorry, that's kind of duplicate, isn't it? Is everyone doing implementation security aware? Do they know about common coding problems in their particular stack? Are you doing functional security tests? A lot of security can actually be tested through sort of straightforward functional testing. Are there good code reviews going on? Are you doing software composition analysis? Is the new posh name for open source scanning, if you've not come across it. Are you analyzing the third-party components you're bringing into your system? And are you doing static analysis of your code? And then, are you taking some accountability for security testing? Are you doing dynamic testing of your system? There are tools that can do that, or there's manual approaches, and there's, are you getting independent penetration testers to give it a good beating? If you're doing all of these things, top job, well done. You're really, a really solid team from a security practice perspective. Most teams I work with don't do all of this. Some of them do none of it, which is really worrying. But I think these are all things you can do very practically in your own teams. And when you come to when you come to secure an API, there's a sort of standard model of how you do it. You make sure you control the volume, that's rate limiting. You make sure you confirm the identity of the caller, that's authentication. You make sure that you can record what happened, that's auditing. You make sure that you check access, that's authorization or access control, and then you call the API function. And of course, you're trying to separate these as much as you can from your API code, so that your API, your function code, does not have security concerns scattered through it, which makes them hard to maintain, hard to check, hard to test. Of course, when you actually come to do it for real, you find that a neat conceptual model like that never survives contact with the real world. Suppose we have an API client, and we've got a process, let's call it a microservice. Oh, let's just call it a service. I hate the term microservice. It's a service running on AWS, and because it's me, it's a Java Spring one. That's just because that's sort of more what I know. But it could be, obviously, could be a C++ one too. And we've got an API function we want to call. You can guess from all the white space, there's quite a lot involved from going from the client to the API function. And the first stage, of course, would be, who are you? Well, the client, I'm assuming here we're going to use an external service for checking the identity, for the authentication. So the client would call the third-party service with credentials probably, and get back a token of some sort to prove the identity of the client. And then would make a call. And at that point, we need rate limiting. So that's where on AWS, for example, you might use the AWS API gateway that has, as well as all the features for redirecting and managing APIs, it's got rate limiting and other basic security built into it. It can act as a WAF, a web application firewall. Then that, of course, would call your process. And inside your process, you'd want to have a number of separate bits of code before your functional code that for security. So in the Java world, these are probably servlet filters. And then you're probably using something like Spring Security or one of the Apache frameworks that, of course, your talk has left my mind. There's an analogous Apache framework which provides a lot of standardized plumbing for this. And all language stacks now, I think, have got security frameworks. So it would go through an authentication filter, and that would probably call back to the external service to say, I've got this person, I'd like an access token for this thing I'm going to call. And it would go, yes, that's fine, here's a token, or it would go, no, they're not allowed to access that. And would return an error, which you could then be thrown back. And then you might want to record the fact that this is about to occur, the fact that somebody has asked for access to this, and we'll check that. And then the way that this probably works is the filter probably writes to a local file in AWS. They have a service called CloudWatch, which, among other things, collects log files. And it's got an agent that would run on the node, and every couple of seconds would take the new entries from the file and send them off to CloudWatch, where they can no longer be tampered with. That's the key thing. Then it would go through an authorization filter to make sure that this person could actually access this resource. This doesn't call back to the service, you'll notice. I'm making some assumptions here. I'm assuming that you're using JWT tokens. JWT tokens are a sort of self-contained token that they're signed and encrypted, and they contain a set of claims. And so the authorization filter can actually check by using public key of the external service. It would have had to call that to get the key back, but it would have done that at startup. It can use its public key to check that the signature is correct, and then it can trust the claims inside the token. And then the authorization filter will check whether you can call this function or not. And assuming it can, bingo, you can call the function. Well, there are a lot of moving parts. But actually, an awful lot of this, I'm sort of showing the innards, really. From an application developer perspective, actually, most of this in the Java world is annotations. You can place annotations on your code, and actually these filters are auto-magically configured by the framework at runtime. The reason, of course, I show them is because it's so important to know what the auto-magic is. And there's a book I recommend at the end, which is actually very good for understanding it. Lastly, you may well have some authorization that can't be done anywhere apart from right at the function. And again, something like the Spring Security Framework gives you more annotations to allow you to do that. But you may need to build a hopefully separated layer which actually does very application-specific authorization very close to the function, because that's the only time you've actually got the state. So you might have to have a method you always call before you, or put a proxy around it or whatever, before you call your final application code. For all of these different pieces, you've got lots and lots of choices. I'm not going to go through them all. I'm sure you know many of these, but just when you look at authentication and authorization, you can build your own. It's generally not a great idea if you do build your own. Obviously, use a framework, but you can build your own. You can use the cloud service ones that are built in. You can use third-party ones that are normally SaaS systems. There are on-prem products, or you can install them in your own cloud, the so-called identity access management products. And there are open source products too. It's sort of the same in all of them. It's a whole range of options. So what are the actual tactics we might use to secure APIs in general? Well, there's sort of 5 of them, which we will go through now fairly swiftly. You've seen bits of this already in all the mitigations. What I'm trying to do here is just sort of bring them together so that they're one piece of content. So key tactic, we've seen repeatedly, don't trust the client, because people can impersonate your client. So beware of everything sent by the client. And just assume that there's possible tampering on behalf of the client. So use a TLS connection to avoid an intercept, man-in-the-middle attack. Use short-lived sessions so that if somebody has hijacked a token, they've only got seconds to use it. Re-authenticate humans or revalidate tokens just before really sensitive operations. Use opaque tokens for IDs so that you can't just guess them. And validate everything all the time. Injection is a problem in most computing environments because we try and make everything general and we try and generate things at runtime to make them flexible. But many things are interpreters, as you all know. Operating systems have got command shells, databases have query processes, configuration files, and anything that does parsing. In the web app API list, for example, it's in the Java top lists. For example, there are significant problems around. No, I think it is in the web app. Significant problems with some XML parsers that will that you can trick them into calling external URLs. So effectively injecting a webhook into your system because it's a parser. It's just following instructions, and if you can give it the right instruction, then it will go and reference an external what it thinks is an XML entity, and actually it's just calling a URL. It's just doing a get. Assume somebody will find your interpreter. Don't assume that it's hidden away. And so don't use string manipulation wherever possible, sanitize strings wherever possible, and always reject very long strings. There's hardly ever a reason to have a very long string in an API. Protect information as much as possible so that when the inevitable breach occurs, there's not so much valuable stuff to be able to actually extract. And so we just assume a perimeter breach. This means encrypting everything possible, but it's easy to say, as you all know, it's much harder to do. It slows everything down. Even symmetric key encryption slows everything down. Once it's queried, querying is really hard. So you sometimes end up with great reduction in the usefulness of the encryption. You've encrypted the main data, but you've got some index off to the side, which allows you to work out which item you want to retrieve and decrypt, and actually the sensitive data in the index. So maybe it's just not worth encrypting it. Maybe you need to look at a different way of protecting it. Sometimes you need to message route on sensitive fields. So you probably have to either use some kind of a proxy for that field, which isn't obvious and can't be mapped that easily. So for example, you map from client IDs to a routing code somewhere so that the client ID is not revealed to the messaging system. But if you can't do that, you may just have to reveal that. Managing and rotating keys is tough. The cloud services are doing a very good job, I think, of making this much easier. Most of them have key rotation schemes built in, especially if you're doing it all yourself. Managing and rotating keys can almost become a career of its own. And of course, restoring data that's all encrypted adds an extra step of complexity. If you've lost all of your primary cloud region and you're going to restore stuff manually from encrypted backups, you're absolutely sure you've got all the decryption keys you need. Simplifying and standardizing is the 5th one. And this is because, as we've said repeatedly, complexity is the enemy of security. Bruce Schneier, very well known, he now calls himself a public policy technologist, but he's a security guy. He's a very well-known security engineer. He has said for years, you cannot secure what you do not understand, and complexity obviously is in conflict with that. In particular, special cases are often forgotten. I've suffered from this a few times in my career personally, dealing with ACL-based systems, for example, where there's some special ACLs grafted in that no one's expecting. And the reason is because there's some special users somewhere that have to be treated specially. And suddenly you've got potential security problem, a potential covert channel, a potential elevation privilege problem. So you simplify, you standardize, and you automate as much as possible, because the simple stuff is easier to check and therefore easier to secure. As soon as you standardize, you beat out a lot of the special cases. But of course, especially in older systems, maybe that's very hard to do because those special cases are being used. And automation removes human inconsistencies, as we said earlier, which avoids one area of risk. So then, just to conclude, a few words on tools. Security tools are obviously useful. I would not take issue with that at all. And the many types exist, from simple to complex. The problem is that you get two unfortunate reactions to them. One, people stop thinking because they go, well, the tool's going to catch the security problems. Or people see there's a tool and decide that obviously no one's going to take security seriously, so they're not going to bother thinking about it themselves. It's very important to stress that the tool is there to support the human thought process, not the other way around. And there's a number of kinds of tools. There are specialist security scanning tools. There's the interactive tools for penetration and exploratory testing. And there's open source scanners, so-called software composition analyzers. Automated security testing. There's four main types of product. There's the static scanners, scan your code, spot things that are likely to be wrong, data flow analysis and so on. Dynamic analysis tools, they run the simulated attacks on test instances of your system. Interactive automated security testing, these are agents that get embedded into your test environments, and they watch out for what look like security vulnerabilities or security problems. So you can put an IAST in and then do a pen test against it, and the IAST agents will spot what appear to be vulnerabilities and report them to you. And then there's RASP, which is kind of related. The difference being IAST is intended to be a test time technology. It's a bit more intrusive, and it's all about telling you what's wrong. RASP is a runtime thing. It's intended for use in production. It's also typically agent-based. It wraps itself around your software. But what it's there to do is to spot a real-time attack and block it. Alert as well, of course, but to block it. The challenges with all these tools are avoiding false positives, especially if you're in production. But even for static scanning, not having thousands and thousands of false positives. And the effort to mitigate them if they're used late in the life cycle. It can really turn people off when people they run a static analysis tool, but they've been working for 2 years on it, and it gives them 20,000 findings. It's pretty demoralizing. Well, I realize I'm somewhat out of time, so I'm going to go straight past most of these tools, which are security scanning tools. I just mentioned open source scanning. If you're using open source, I think these things are really quite important, and they're really useful tools. They scan your code base, they fingerprint, as in create, identifying fingerprints from your binaries, and then query central databases, SAS databases, for known vulnerabilities or risks to do with those components. And then obviously they have nice reporting and dashboards to let you see what's going on. Given the complexity and the amount of manual effort it takes to stay on top of your open source dependencies, I think these tools are extremely useful. Unfortunately, they're all commercial, and that's because not so much the software is hard to develop. It takes a lot of time and effort to create the databases and keep them up to date. There's four big vendors I'm aware of in this space: Synopsys, Black Duck, White Source, Sonatype, people of the repository fame, and SNCC, who are quite a new vendor. I'm not recommending one over the other. At Endava, as it happens, we use Black Duck, but we've looked at all of these, and they're all very capable tools. So in summary then, the OWASP API Top 10 is a fairly new piece of research from OWASP to try and identify the 10 most dangerous risks that they see in the wild with APIs as of 2019. There were probably many of them were quite familiar from the web app security from your own experience. It's not so much maybe that you need to be reminded, but these are the things that it appears that experts and quantitative analysis suggest you should be stressing with your teams on a day-to-day basis. Some of the key aspects of actually dealing with security are preventing injection, ensuring that validation is done constantly, ensuring that implementation is done carefully, and that certain obvious problems such as bulk binding people are aware of, and making sure that people are thinking about the environment their software is going into. And if they're not controlling that themselves, they're working with other people to make sure that you're rate limiting, monitoring, logging, and so on. An API conceptually is secured by using rate limiting and authentication and auditing and authorization before you get to the API function. It's quite clear that when you actually try and do it with real tools, real technology, real frameworks, this model is a little bit too neat to be true. But I find it's a really useful internal kind of, if you like, a reference design, a reference architecture for how this should work. Is that if you're not doing those four things, you've got a problem. And if you're not separating those four things as much as possible, you've probably got maintenance problems and potentially security problems. I think it is a very useful model. And as we said, our tactics are don't trust clients, injection, 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 protect information, simplify and standardize and automate. And finally, I realize I'm just out of time, but a number of books that I'm currently recommending about security, software security in general, API security in particular. You'll notice if you come to one of my talks before, I've actually refreshed the book list quite a lot. That's because it's really, really positive. There have been a lot of good security books written over the last 3, 4, 5 years. And I first put together my book list probably 7, 8 years ago, and I've refreshed it a little bit since. The books I used to recommend, I think, are still very valid. There's still a lot of wisdom in them. And if you look past the detail of the samples, what they're saying is still absolutely true. These books are just a little bit newer. The Shostak book, for example, I've been recommending a long time, but there's now a new threat modeling book from O'Reilly, which I've read it recently. I think it's really good. It's just another view of threat modeling. It's got a much more objective view of the different ways of threat modeling, whereas Adam Shostak's book is very much his approach to threat modeling that they use at Microsoft, the stride and dread stuff. Ross Anderson's classic is now, he's about to ship his 3rd edition. The 2nd edition is now freely available on his website, his 3rd edition. And an all-round software security book that I think is fantastic is the Laura Bell, Michael Brunton-Small, Rich Smith and Jim Bird book. I think all those people worked for GDS in the UK at some point. Certainly Mike Brunton-Small did. He worked with a friend of mine. He was there. They've written a really nice book on how to take security into modern agile software development, but still make it real security. I think that's one of the best security books I've come across. And the other books are great too. I'll give a quick shout out for the 2 Java people in the audience. Java Security in Action is written by one of my colleagues, Larry T. Spilker. But all of the other books have something to offer. One I'll just also mention is API Security in Action. I'm afraid it's also very Java-centric, so the C++ people might get less from it, but it shows you how to build API security from the ground up. And this little model actually sort of came from his book. So although you wouldn't necessarily want to do everything that book shows you how to do, you come out of that book with a really good understanding of the nuts and bolts of how all of these magic security frameworks all work. So, thank you very much. I hope that was instructive. I hope it was not too boring. 90-minute virtual presentations, quite a thing to sit through, and I can assure you quite a thing to present. So thank you very much for attending. I'm really happy to take any questions which I think will have to be by chat, sorry, because of the way the webinar is set up. But otherwise, I hope you enjoy the rest of the conference.